Homological algebra, the essence of homology and cohomology. Homological algebra is a branch of mathematics that delves into the study of homology and cohomology theories. These theories equip mathematicians with powerful tools for analyzing and classifying mathematical objects like topological spaces, groups, and modules. The fundamental idea behind both homology and cohomology is to associate algebraic structures, such as groups or rings, with these mathematical objects, thereby extracting valuable information about their properties. Homology, a concept originating from the study of topological spaces, involves analyzing a space by examining its cycles and boundaries. Cycles can be thought of as closed loops or surfaces within the space, while boundaries are those that can be reduced to a point within the space. 1. Chains and complexes. To start, we consider chains, which are formal sums of elements from the space. These chains are organized into chain complexes, sequences of abelian groups or modules connected by boundary operators. These operators map one chain to another, capturing the idea of moving from higher dimensional elements like surfaces to lower dimensional ones, like loops. 2. Cycles and boundaries. In this framework, a cycle is a chain that maps to zero under the boundary operator, meaning it has no boundary. A boundary, conversely, is a chain that is the image of another chain under the boundary operator. The key idea is that cycles represent significant features of the space, while boundaries represent trivial features. 3. Homology groups. Homology groups are constructed by taking the quotient of the group of cycles by the group of boundaries. These groups, denoted as h_n for the nth dimension, measure the holes or voids in various dimensions within the space. For example, h_0 represents connected components, h_1 represents loops, and h_2 represents voids or cavities. Cohomology is a related concept, but offers a slightly different perspective. While homology focuses on chains, cycles, and boundaries, cohomology deals with cochains, cocycles, and coboundaries. 1. Cochains and complexes. In cohomology, we work with cochains, which are functions that assign values to chains. These cochains form cochain complexes, sequences of abelian groups or modules connected by coboundary operators that act in a manner dual to the boundary operators in homology. 2. Cocycles and coboundaries. A cocycle is a cochain that maps to zero under the coboundary operator, implying it assigns zero to boundaries. A coboundary is a cochain that is the image of another cochain under the coboundary operator. Like in homology, cocycles represent significant features, while coboundaries represent trivial ones. 3. Cohomology groups. Cohomology groups are formed by taking the quotient of the group of cocycles by the group of coboundaries. These groups, denoted as h_n for the nth dimension, provide an algebraic classification of the space that often carries additional structure. Cohomology groups are particularly useful because they come with additional operations, such as the cup product, which provides a ring structure on the cohomology groups. Applications and importance. Homology and cohomology theories have extensive applications across various fields of mathematics and beyond. Some notable applications include 1. Topological invariants. Both homology and cohomology groups serve as topological invariants, meaning they remain unchanged under homeomorphisms. This property makes them essential tools for classifying and distinguishing between different topological spaces. 2. Algebraic topology. In algebraic topology, these theories bridge the gap between algebra and topology, allowing topological problems to be translated into algebraic ones, which are often easier to solve. For example, the famous Euler characteristic can be computed using homology groups. 3. Geometry and manifolds. In differential geometry, homology and cohomology theories aid in studying differentiable manifolds. They provide insights into the structure and properties of manifolds, including the classification of vector bundles and the study of characteristic classes. 4. Singularities and intersection theory. In algebraic geometry, these theories help study singularities and intersection theory. They aid in understanding how different algebraic varieties intersect and behave near singular points. 5. Physics and string theory. In theoretical physics, particularly in string theory, these mathematical tools are used to analyze the properties of spacetime and the fields defined on it. Homology and cohomology theories help in formulating physical theories and understanding the topology of the universe. Advanced concepts. Beyond basic definitions, there are several advanced concepts and extensions of homology and cohomology theories. 1. Relative homology and cohomology. These extensions consider pairs of spaces. Relative homology and cohomology provide more refined information about the structure of a space relative to a subspace. 2. Derived functors. In homological algebra, derived functors extend homology and cohomology theories to more general settings. They offer a systematic way to study various constructions in a homological context. 3. Spectral sequences. Spectral sequences are tools that help compute homology and cohomology groups in complex situations, breaking down complicated problems into more manageable pieces. 4. Sheaf cohomology. In algebraic geometry and complex manifolds, sheaf cohomology allows the study of cohomology with coefficients in sheaves. This theory has deep connections with various areas of mathematics, including number theory and complex geometry. Conclusion: Homological algebra, through the lenses of homology and cohomology, offers a robust framework for understanding and analyzing the properties of mathematical objects. By associating algebraic structures with these objects, homology and cohomology theories enable mathematicians to classify and distinguish between different structures, solve complex problems, and uncover deep relationships across various fields of mathematics and science. Whether in topology, geometry, or theoretical physics, these theories continue to be fundamental tools driving progress and discovery.